It's really great to be here. This is probably my favorite conference. So yeah, thanks a lot, everybody who helped organize it. So I'm going to present some joint work with Mark Howard, Earl Campbell, and Vadim Klichnikov, who's also at Microsoft. And I would like to mention Vadim. He would really have liked to have been here, and had he been able to come, he would have presented this work himself. He was really the driving force behind this project, and he's sad he couldn't make it. The reason, if you're interested, is because of green card purgatory, which is something that affects many of us researchers in the US. It's very annoying. Okay, so today I'm going to be talking about the cost of algorithms, the cost of different algorithms that we could implement with quantum computers. And before we launch into the specific type of cost that we use, I want to take a step back and think about what should a cost do for us. So what we really want is we want a cost function for an algorithm which somehow reflects the physical difficulty of implementing the algorithm in a scalable, fault-tolerant quantum computing setting. But we also want it to be very abstract. We want a notion that allows someone to give you, say, logical level circuit description of the algorithm, and then for you to simply establish what the cost of that algorithm is. So we want something mathematically well-defined and abstract, and that will allow us to say very general things as well. So the kinds of costs that you might think of in this setting, the first one that probably comes to mind is similar to what people use as standard in the classical computer science field, circuit depth. How long is the circuit that performs your algorithm? There's some disadvantages for us in that particular kind of cost metric. One of them is the circuit depth. Well, for a start, it doesn't take into account how many qubits your quantum computation requires. And we know that, at least for the foreseeable future, having a large number of qubits is going to be a bottleneck. So maybe we should instead look at the circuit width, which of course is the number of logical qubits in the algorithm. But that's probably a little bit too coarse as well. It doesn't account for the length of the circuit, the amount of time that it would take. So circuit area is the natural generalization of these things, which considers both the length of the computation and the width of the computation. So that's a little bit better, but it's probably still too crude for us. We know that for a start, in order to even specify the circuit area, we need to state in our algorithm what the set of gates that the algorithm is implemented using is. And also, we should take into account the fact that some gates are likely going to be much more difficult to perform than others. So this has been considered before, and some of the early work in costing of algorithms has focused on C0 count. So instead of looking at the total circuit area, you ignore the single qubit gates and you kind of focus on the multi-qubit gates, presuming that they'll be more expensive. And this is a very reasonable scenario at the physical level in hardware. Usually, indeed, it is more difficult to implement entangling gates than it is to implement single qubit gates. But that's not what we're interested in, because we're interested in taking a logical algorithm and working out the physical cost of that when you use fault tolerance and error correction. So maybe C0s are not the right thing. So when we look to fault tolerance, to the literature, what do we learn? Well, of course, there are some well-known results by Easton and Knill that tell us that the easy gates, the transverse gates in any quantum error correcting code are not enough. So there will be some gates which are difficult to implement at the logical level, and some gates which are easy. Moreover, if you put physical restrictions on the system, for example, if you require that you lay things out in 2 dimensions and have geometrically local operations, the setting that Alex was talking about, for example, then the gates that are easy will all be Clifford gates. So that's very restrictive too. And this isn't necessarily a terrible thing, because we know from early work by Bravy and Kitaev and also by Knill that if you have stabilizer operations, so these Clifford gates, and also preparations of basis states, logical basis states, and of single qubit Pauli measurements, then that is in fact enough to perform universal quantum computation, provided you can also produce noisy magic states, which I'll come back to in a second. So the point is, this is a barrier, but it's not the end of the story. We can still do computation in quantum computation in this realistic setting. But the production of these magic states, which are required for universal computation, in addition to the stabilizer operations, which are relatively easy, that's very expensive. These magic states are expensive to produce. So to kind of summarize this, and this will be familiar, I would imagine, to most people in the audience, the general framework is we imagine that our quantum computer, our fault-tolerant quantum computer, can relatively simply perform stabilizer operations, so Clifford gates, Pauli measurements, and also generation of basis states at the logical level. And then you feed in large numbers of noisy magic states, which I represent here in this picture. And those, using stabilizer operations, are distilled into a much smaller number of clean magic states over here. And then you can use that with a gate teleportation gadget, which uses only stabilizer operations, in order to apply this gate, which is non-Clifford, and thereby completes the set of universal gates that you need in order to implement your quantum computer. But you can see here, and I've kind of underestimated how many inputs there need to be to this algorithm. This is really why producing these clean T states is so expensive, because this distillation procedure requires a large number of inputs. So the cost that I would like to use in this talk is really motivated by these fault tolerance and error correction considerations, and we're going to take the stabilizer operations as being completely free. We're not going to count them at all. And we're just going to count how many copies of T are required for some algorithm. And I'd actually like to be a little bit more general than that. Instead of just T states, I'd like to consider other states which, like T, cannot be produced by stabilizer operations, and also, like T, can be used to implement gates, non-Clifford gates, and thereby completing our universal set of gates. So some examples of these that will come up in the talk, and there'll be even more in fact, are the square root of T. So the T gate is produced by, or the T state is produced by applying T to the plus state. The square root of T gate state is produced in an analogous way. And in fact, they're all like this. So this is the control phase gate here, CS, also a non-Clifford gate. And that is produced by just applying, since it's a 2-qubit gate, CS to a pair of pluses. Okay, so that's the cost metric that we're going to consider, is number of non-stabilizer states required for some particular algorithm. And we're going to be interested in looking at the cost for general tasks. So what I mean by that is, imagine you have some task like, I want to apply a multiply controlled Z operation. And of course, this is a useful task. It's used in the reflection step of Grover and many other standard quantum algorithms. So if this is the task that we want, there might be many different algorithms that perform this task, which I've kind of generically drawn here as an illustration, each with a different cost. And in this case, I'm imagining the cost is in terms of this multiply controlled Z state, this CCZ state. And then we're interested, of course, in the one with the lowest cost. And we can ask about upper and lower bounds of this optimal, this cheapest possible algorithm for this task. So an upper bound you can find as soon as you find an algorithm which implements the task, of course, right? If you find an algorithm that implements the task and you know the cost of that, then that's an upper bound for the best possible cost. So finding an algorithm gives you an upper bound automatically. And for example, for this particular task of applying the C, so this is controlled on n minus 1 qubits, you apply a Z on the last qubit. This Craig Gidney has an algorithm for this presented in 2018, which requires n minus 2 copies of the CCZ state in order to implement. So we have an upper bound for that. And then lower bounds, they are kind of infamously difficult, and you can imagine why, because it's not enough to just have one algorithm which works. You have to somehow prove that there can exist no algorithm at all which is better than a certain amount. And that is a lower bound. And as we'll see later, for this particular task, we can prove that you need at least n over 3 copies of the CCZ state. So why care about lower bounds and upper bounds? Well, the way that I like to think about it is upper bounds are useful for convincing us or other people that they should try and build quantum computers. If there's some task that they're interested in doing, for example, simulating some large molecule that might make them lots of money, then if you can upper bound the resources, the cost that will be required to build a quantum computer to do that, then if that upper bound is sufficiently low, they know that's the most they're going to have to pay, and so they might decide to do it. So it's good for motivating the field and motivating people to build quantum computers. On the other hand, lower bounds are useful if you've already decided you are going to build a quantum computer and you want to get the most out of it. You want to see, can I do better? Are my algorithms optimal, or can I still maybe improve them? And I would argue, given the fact that, well, maybe the field is being flooded with money these days, maybe lower bounds are more relevant at this stage in the development of quantum computing. It seems like the world has been convinced that they should try to build quantum computers. So probably we're in the realm where lower bounds are very useful. And this talk is about lower bounds, so I'm clearly just trying to sell my talk. Okay, so the things that I'm going to cover here essentially are, they split into 3 types of task that I would like to look at. So the first type of task is converting between resource states. So that's kind of the simplest task you can imagine. I start with some number of t states, and I want to produce some other type of resource state. And then we'll move on to something like I mentioned before. If you have some very specific unitary, like the multiply controlled Z gate, then what are the lower bounds and the cost required for that? And then we'll go on to something which is a little bit more delicate. If you have a very general arbitrary unitary that you would like to approximate, then lower bounding the number of resources that are required to approximate that generic unitary to within some precision. And then finally, I'll briefly touch on some further restrictions that we get, some tighter lower bounds that we get if we actually, instead of looking at arbitrary stabilizer operations, we restrict to a subclass of stabilizer operations, which turn out to be quite common for many of the algorithms that are known. Okay, so let's start with the resource state conversion part. So here I'm imagining, as showed before, these different types of resource states, so states that cannot be produced from stabilizer operations and moving in between them. And it's a great place to start because it's the simplest thing you can think of analyzing in this setting. But it also should be useful for the whole framework. If, for example, we have some task and we establish a cost in terms of t states of that task, it would be nice to compare and be able to relate that to the cost for the same task for some other algorithm for the same task, which implements it in terms of CCZ states or CS states or some other resource state. And also, we see this as being potentially more broadly useful outside of this framework as well. For example, if you have 2 different distillation schemes and you want to compare them. So pictorially here, you can imagine that I have a distillation scheme A, probably developed by Zhangwan Ha, for T state distillation, and then I have another distillation scheme probably developed by Zhangwan Ha for CCZ state distillation, and I want to compare them. Well, if we have a way of relating CCZ states to T states, then of course we can make a new T-state distillation scheme from B by first converting T's to CCZs and then converting the output from CCZ back to T. So it allows potentially for the comparison between different distillation schemes, etc. So it's a great place to start. And our hammer, the tool that we will use in order to analyze this setting and others in the talk, is going to be a particular type of monotone, the nullity, which I'll describe now. So first, we often think about the stabilizer of an error-correcting code. Here, I want you to think about the stabilizer of an arbitrary quantum state. So if you have some state, just write down all of the Pauli, it's an n-qubit state, write down all of the Pauli operators on n qubits and check which ones stabilize the state. So have the state as a +1 eigenvalue, or eigenstate. And then the nullity is extremely simple. You just take the size of that group, take its log base 2, so how many generators does the group have, and then subtract that number from the number of qubits. So this is going to be our tool. It's very simple and surprisingly powerful. And some properties that the first two are easy to see. The third I will go into in a second. So this is non-negative, and in fact, if it's 0, then it means that the state must be a stabilizer state. And people who work with stabilizers will not be surprised by that. If you have n independent stabilizers, stabilizer operators for a particular state, then it's completely fixed. It's a stabilizer state. It's also additive, and this is pretty easy to see. If you imagine taking two states and tensoring them together, then the total number of qubits in that pair of states is just adding the number of qubits in the first state to the number of qubits in the second state. And the stabilizer group of the overall tensor product state is just the product of the two stabilizer groups. So when you take the log of the size of that, then they just add. So this nullity monotone is additive. And then the last property, which is going to be the one that's really valuable for us, is that it's monotonic under stabilizer operations. So what I mean by that is if you start with some state psi in, and then you use stabilizer operations to produce some other state psi out, then you will know for sure that the nullity of the input has to be at least as large as the nullity of the output. And so before we go on to showing why this is true, just to see why this is a useful thing in the first place, it's very simple to calculate the nullity of the T state and the CS state. You just check a few Paulis, and you find that there are none which stabilize these states. So the nullity of T is 1, the nullity of CS is 2. And therefore, this tells us that the T cost of producing the CS state must be at least 2. It's impossible to produce a CS state with fewer than 2 T states. Because, just to kind of make sure that we're all on the same page, if the nullity of a single T is 1, it's less than 2, so you can't use a single T to produce CS. By the additive property, the nullity of T tensor T, so 2 copies of T, is 2. So that may be possible by this argument. Okay, so why is this a monotone under stabilizer operations? So let's remind ourselves of the stabilizer operations. We have Clifford gates, we have basis state preparation, and we have Pauli measurements. So the first two are pretty easy. Clifford gates, if I have a state and I apply a Clifford operation to it, then the set of Pauli operators which stabilize the state will be transformed, because Cliffords take Paulis to Paulis, into a new equally sized set of Pauli operators which stabilize the new state. So the nullity will be unchanged if I apply a Clifford operation. If I introduce a basis state, then by the additive property of the nullity, then the new nullity is just the nullity of the two states added together. But because a basis state is a stabilizer state, it has 0 value of nullity. So the nullity is unchanged when we introduce basis states. So the last thing is measuring Pauli operators. That's the other stabilizer operation that we need to consider. And so I'd like to just talk this one through. So if you measure a Pauli operator P, then there are two cases. The first case is that P will anti-commute with some generator, some element of the stabilizer of the state. Okay? And if that's the case, then we can imagine writing all of the stabilizers, we can imagine writing the generators of the stabilizer of that state. And we can always choose a set of generators so that only one of them anti-commutes with P. Because if some other ones anti-commute with P, we just multiply them by another one which anti-commutes with P and get a new generator. So we have a set of generators, one of which anti-commutes with P. And all the ones which commute with P, when we measure P, will be unchanged because they commute with P. And after we measure, P will now be satisfied, but the generator which didn't commute with it will no longer be satisfied. So we have a new stabilizer group which is exactly the same size as the original one, so the nullity is unchanged. And in fact, because we went from a set of P's being stabilizing the state to another set of P's stabilizing the state, this just implements a Clifford operation on the state. So the other case is where P commutes with every element of the stabilizer, and then this splits into two subcases. So the first is that P commutes with everything in the stabilizer because P is actually in the stabilizer. All elements of the stabilizer commute with one another. And then, of course, when we measure something which already is satisfied, when we measure an operator that's already satisfied, it doesn't change its value, so nothing changes, so the nullity is unchanged. And if P is not in the stabilizer, but commutes with everything, then because it commutes with everything in the stabilizer, the other operators are still satisfied afterwards. But we know that after measuring this new operator, it will be added to the stabilizer. So the stabilizer has to get bigger. The weird thing for those who are paying close attention is it doesn't just double the stabilizer necessarily, which was surprising initially to us. Okay. So let's go back to our analysis using this tool with our particular example. So we can now consider lower bounds for the t cost of producing CS. We already discussed that. It's 2. But there's some other things that we can do as well. The first is that by additivity, we can also consider the kind of asymptotic, the rate case for this very easily, because it must also be that to produce n copies of CS requires 2n copies of t, just by the additive property of the nullity. And we can flip it around and say that actually if we started with CS and we wanted to consider producing t states, then if we have n copies of t, we won't be able, just by the nullity, we won't be able to produce, the cost of producing n copies of t will be at least n over 2 copies of CS. Okay, so this is a set of bounds. And then now we can consider how close these are to the upper bounds, which we get from specific algorithms. So the t cost of producing a CS, which we know is lower bounded by 2, there exists an algorithm shown here, I'll talk through it in a second, which requires 3 t states to produce a CS state. So this is just a circuit identity for the controlled phase gate in terms of t's and a t dagger. And this has been known for quite a long time. And you can imagine, to make this clear why this applies to states, imagine applying both sides of this circuit identity to the plus state. Then the left would literally be the CS state, and the right would be this right-hand side part of the circuit applied to 2 t states. And we can inject, using a single additional t state, this t dagger part here. So indeed, this gives us an algorithm for producing the CS state from 3 copies of t. So what about the other way around? To go from CS to t, well, you can show by a ring argument that I'm going to discuss quickly now that it's actually impossible to do this. There's no number of copies of CS that will produce, that will exactly produce a t state. So how does this argument work? It's actually quite straightforward. So we can just imagine writing each of our copies of CS as a vector, which is this one, and then we can go through the different stabilizer operations and what they correspond to acting on these kinds of vectors. So the first is if we introduce a basis state, then we just tensor on this vector here. And the Clifford gates are generated by the Hadamard, the phase, and the CCZ gate, which are all represented here as matrices. And applying Clifford gates will just multiply by these matrices. And measurement corresponds to multiplying by these projection matrices here. But notice all of the entries of these matrices, other than this global phase here, are just ones and i's, and pluses and minuses of those. So it's pretty clear that you'll never be able to generate this entry in any of your multiplication and tensoring operations, which has this phase, e to the I pi over 4 here. And so this argument can be generalized, and we have a much more general version of it in the paper, but it's really fairly straightforward that you can't go from CS to T with any number of copies of CS from this. But there's a trick to get around this, and that is to use catalysis, which is something which has been known to Earl Campbell and Craig Gidney, I think, for a little while. And the idea here is, so we started. This is the circuit I already showed you. But if we note that this V part of the circuit here, if we multiply both sides of the circuit by its inverse, then we get this relation here. And now I consider applying this to plus states. What you then get is you get two T states going to a CS state and a T state. Or you can implement it by using a CS state and a T state. So in other words, the kind of chemistry equation we might write is a CS state and a T state produce two copies of T. And the fact that we started with a T here is what gets us around the ring no-go proof that we just went through in the previous slide. We borrow the T, we somehow magically get that extra phase that we need, and then we give the T back. So we represent these kinds of reactions as with a double arrow to indicate there's some other catalyst which is being borrowed, some other state. And fortunately, the additivity property of the nullity comes to our rescue again. Nullity, anything which is ruled out by nullity without a catalyst being considered, will also work for a catalyst, simply because if you have some state A and a catalyst, and you want to consider producing some state B and a catalyst, then by additivity, the catalyst, the nullity of the catalyst just adds to both sides of the equation and cancels. So nullity will still work for this. Okay, great. So this is what we've already established with the nullity. We know that in this rate equation, so to get from T to CS with or without catalysis, then we need at least 2 T states. R should be 2. And similarly, to go from CS to some number of T's, we know that this R primed can be at most 2. We can get at most 2 T's out. And then this is not the only monotone for stabilizer operations. Another one which is very useful is the extent, which was previously introduced by this set of authors. And the extent gives some other bounds for the same process, and crucially they're different from the bounds that we get from the nullity. And the bound that we get for the first reaction or the first direction is better, it's tighter, and the one that the extent gives for the other direction is looser. So we of course take the best of both. And then you see that well, first of all, the 3 and 1 here come from the upper bounds. So those are the known algorithms that we know how to produce from 3 T states a CS state, and from 1 CS state a single T state, the algorithms I just showed you. So we know from that if you start with 3 T states, you can produce a single CS state, and then starting from that CS state, you can go back to a single T state. But there's been loss. You started with 3 T states, and you ended up with 1 T state. But it's not just that we haven't found optimal algorithms. By these bounds, we see that this loss is unavoidable. If you start with any number, even in the asymptotic limit, of exact T states, and you go to CS states, and then you go back again, you'll have fewer than you started with. Um, it's a good thing you can't see this. So the the highlighted part of this table is what we've discussed. It's just an example. Of course, we go through lots of other states. That's the main point of this slide. And we also have other results in this area, which, first of all, we have, as I mentioned before, a more general version of that no-go theorem than that I argued earlier. But we also have two new families of conversion algorithms based on the phase polynomial framework and also on the one-bit adder, which generate conversions which would only work with catalysis. They wouldn't work without catalysis. So we have no-go, and then we have families which get around that no-go in this conversion framework. Okay, so let's move on now to the cost of implementing a specific unitary, and this is really a very simple extension of what we've already discussed. So the idea, and we should take a second to think about this, the idea is, suppose that you can implement this unitary, and you can do it using m copies of some resource state. Then, because you can do that with m copies of the resource state, you could just apply that unitary to the all plus state, and you could produce this state here. So what we can do to prove a lower bound for the production of this unitary is use the state lower bounds that we've already been working on. So that's just saying the converse here. If we can't produce this CS state using m copies of psi, then we also can't produce the unitary, just from the converse of the above. So it turns out that it's possible for arbitrary n to calculate the nullity of this C multiply controlled Z state, which, as written up here, is just the multiply controlled Z gate applied to the all plus state, and it's n. And so that immediately gives us bounds on how many T's, how many CS's, and how many CCZ's would be required to implement the gate multiply controlled Z. So for T, because the nullity of T is 1 and the nullity of this state is n, then the lower bound is n. For CS, it's n over 2. And for CCZ, it's n over 3. And this is the setting that I mentioned before, that there is an algorithm for which requires n minus 2 copies of CZ, which is where the upper bound comes from. Okay, so another specific unitary that would be interesting to analyze is the adder circuit. It's also used a lot in many quantum algorithms, particularly in oracles. And the adder circuit really just takes two inputs here, not single qubit inputs, but n qubit inputs, and for each of the basis states, it just adds them together. So it outputs the first input being the same, and the second input being I plus j modulo whatever the number of states that can be contained in n qubits is. Modulo 2 to the n minus 1, I should say. So this looks a little bit ugly, I apologize, but let's define a state, the quantum Fourier transform, the quantum Fourier transform state here, which is really just the sum over all basis states with particular phases associated. And it turns out that this can be written in a product form here, a tensor product form. So something that's relatively straightforward to show, and we were not the first to show it, is that if you apply the adder circuit to the first input of the adder being the all plus state, and the second input being the quantum Fourier transform state, then what is output is just the quantum Fourier transform state on the second input, and the first input is the same state but complex conjugate. And so using a very similar trick to the one we just discussed, we can think about what this implies in terms of state conversion. So this therefore implies that if we had if we were able to implement A with m copies of some resource state, then we would be able to catalytically convert between m copies of that resource state and the QFT star state. That's literally what this equation is saying. This part is implemented with m copies of psi, and this, and then we would produce the right-hand side, but QFT appears on both left and right, so it would be a catalytic conversion. But we can calculate the nullity of this, and this is easy to calculate precisely because of this tensor product form of the state, because we can calculate for each of these states. The first two of these for the small k are stabilizer states, and then the rest are not. So the total nullity of this state is just n minus 2. And that gives us our lower bound for this case. Since the nullity of CCZ is 3, we get n over 2 minus 3 is our lower bound of the number of CCZs. Okay. So now we go on to the more difficult case, which is the arbitrary unitary approximation. Okay, so our goal is going to be, suppose someone gives you a specific single qubit unitary, and they ask you to approximate that unitary using stabilizer operations and some input stabilizer states, some copies of psi. Then how many copies of psi do you need in order to achieve some diamond norm precision epsilon? And the bound that we're going to get is the lower bound that we're going to get is the left-hand side here, which you can see on the right. This is an explicit algorithm. It's the best one known to date, which was by Ross and Selinger in 2016, I think, but also using some more modern techniques that were introduced by Earl Campbell and independently by Matt Hastings to mix unitaries. So this is the best algorithm that we know of. So this is an upper bound, and this is a lower bound that we produce here for this problem, where, of course, we're imagining that U is the worst case. It's the hardest one to, it's the hardest unitary that can be implemented. So there's some things I'd like to mention. There have been lower bounds before for this setting that people call sometimes unitary synthesis. And the reason that our set, or the way in which our bounds are stronger, is because we have a much more general scenario. So in the previous bounds, there are a few different ones, but for example, they didn't include measurements, and if they included ancillas, they only included a few ancillas. But what we are able to do is apply this to the very general setting that we care about. We have arbitrary measurements. The measurements can be used as controls for later parts of the circuit. You can have as many ancillas set to stabilizer states as you want, and these bounds will hold. Unfortunately, the strategy that we used before won't directly map across to this setting. Our monotones don't help here, so we use a different technique, which I'll go into in a second. And there's also some random variable subtleties here. Because these bounds apply to settings where you have measurements that may control subsequent parts of the circuit, you might, in some runs of your algorithm, use a different number of t-states or whatever type of state it is than in other runs of your algorithm. So there's some random variable aspect here. And you can see the bar I have over n. That's really what that means. This is an average case. And the approximate strategy that we use is maybe not too surprising. So the first thing is we show that if you can implement a unitary U to within diamond norm precision epsilon, then you can also make some particular state, U times 0, to within the 1 norm delta, which will depend on epsilon. So we're relating unitaries to states again, as was our strategy before. And then the other thing, the next thing that we do is we say that state is hard to generate unless you have a certain number of copies of a resource state. And in particular, the resource state or the state that's going to be hard to generate is whenever U is really close but not quite the identity. And that's, in fact, the reason that our monotones don't help us here, because our monotones don't diverge. If you take the nullity of a particular state and you take the state going to 0, or you take the extent of a state and take the state going to 0, neither diverge, which is precisely what we need in order to prove this kind of a bound. We need things to get harder and harder as you get closer to the identity. And the first part, there are some techniques that you can use to deal with that. So what do we do? Well, the first thing that we do that we think is of probably of independent interest, is that we introduce a standard form for these kinds of Clifford-based circuits. And this is very useful for us. So it essentially says that if you have a particular stabilizer circuit with some input and some output, then you can put it into a standard form where you essentially replace whatever your stabilizer circuit was by a circuit which has a set of commuting measurements first, commuting Pauli measurements, and then a Clifford. And so you can always do this, and we also know how many commuting measurements there can be. There can only be this number of commuting measurements here in some range, but it's a small finite number. And so what does this do? Well, it essentially takes what seemed initially like an infinite space of things, because we could have an arbitrary number of ancillas, an arbitrary number of measurements, and it makes us have a very finite set of things that can happen whenever we implement a stabilizer algorithm like this. Okay, how many? 0 time? Okay, cool. So, yeah, well, I guess that's I've probably said enough anyway. Essentially what you can do then is you can show that if you have a unitary that you want to approximate, and the state u times 0 is a state that's very close to 0, then if you only have a finite number of copies of a resource state, then you can't get close to it, and you need to increase the number of copies of the resource state, and you can lower bound the one that's closest to the identity, and that's where the bound maps out from. Okay, I will mention this still, even though I'm on -1 minute. So we have some tighter bounds in the setting where all of the measurement outcomes of the algorithm are 50-50. And this, of course, is never going to be a general quantum computation, because if all of your outputs of your algorithm are 50-50, you get no information. But a lot of subroutines are like this. So a lot of scenarios where you have a subroutine which takes a quantum state in, outputs a quantum state, will be built up of stabilizer operations and maybe some other resource states where all the outcomes are 50-50. And in this setting, actually most of the algorithms that are known for the settings that we looked at are of this type. And if you restrict to this, using the techniques that we develop in this section of the paper, many of the bounds become tight. And I would just like to point to one bound which didn't become tight. It was 1 away, but 6 days after our paper came out, we got an email from, maybe unsurprisingly, Craig Gidney, who realized that we could actually use one of our bounds to improve our other by precisely 1, so that his algorithm was optimal. And to close, this came up earlier in the discussion session. So something that I think is worth pointing to in our paper is, it's a long paper, but at the end, in the conclusion section, we have a long list of open questions that could be of interest to some people. Thanks.
So I think maybe we can have one quick question before the break.
Sorry.
Well,
I should have gone longer.
I have a question, maybe more broadly, which is, have you thought at all, these things are all just about counting t's, the number of t's or other states in the relationships, but is there anything about the time ordering, the amount that you can trade off between space and time, that comes out of this way of thinking?
Not that I'm aware of. In some sense, that's kind of one of the things that we try to wash out. We try to remove everything except for the number of copies of a resource state. So yeah, we definitely didn't look at that. I don't see any obvious way of incorporating it to see a trade-off, but it could be interesting. Yeah.
Great. One more, Ken.
I just wanted to say on the list of resources, and I'm curious about your opinion on this, Mike, which is at least a lot of the algorithms we looked at, like I looked at with Fred Chong and Margaret, there's some points where like the communication cost begins to compete with the t cost. So the amount of resources you need to have, so you have some t factors hanging out, but then you need these resources to have enough bandwidth to get this part of your quantum computer to talk to this part. Do you have any ideas on like how we could structure general algorithms? Like it's such a trade-off between the actual mapping the algorithm to the resource. So should we, like what point should we look at that?
It's a good question. Do you think that's a fundamental limit? Are there clever techniques that can allow you to teleport between different parts of the quantum computer to kind of make the bandwidth issue not a problem?
Yeah, it
Depends.
depends on the cost, what you think the cost of memory is.
Okay.
So in one sense, you could always like pre-process all of your entanglement distribution at the beginning, and then count from there. But then that, yeah, depending on what your memory processes, requires those resources to get larger.
Yeah, it's a good question. I definitely don't think that just taking non-stabilizer resources is the be-all and end-all cost that we should consider. But I think it's of the very simple ones to analyze, it seems like a pretty reasonable one. It seems more motivated to me than C-naught cost, for example. But yeah, it's a good question how you should go beyond to kind of incorporate other costly things, or maybe more costly things. Yeah. Thanks.
Okay, let's thank Michael again.